Happy Procedural Generation Day! No, I just made it up. But today I'm going to show you some procedural generation, or at least how I do procedural generation within my engine. We need to start with something simpler. And I need to give you more context about what am I using for procedural generation. So the name of the technique is called shape grammars. It's nothing new. It's actually quite old. It comes from the 1970s. The idea is that you have a grammar that you process, like you have this an ML language in this case. It has an axiom, a starting point, and then you iterate over a set of rules, and you start generating terminal symbols, basically, right? And those terminal symbols are the output of your procedural generation. If we were parsing strings, that outputs would be strings. But in this case, the symbols we are outputting are actually 3D grids of voxels that then are being combined together and forming some bigger voxel thingy, right? So the first thing I need to show you is the actual language that we are going to be parsing in order to dynamically, like on runtime, generate things on the screen. I didn't come up with this syntax in particular. The syntax is based mostly on this project I will be linking now below. The rest of the implementation I had to make myself because this is tailored towards meshes, and the generation of voxels differ in several aspects. So yeah, I had to make my own implementation, but if you want a good reference and look at the code and see how it works, then I really recommend looking at this. Okay, so this in particular is an L system. It's also a grammar and like a subset of the shape grammar I have. And in particular, this is, like you can see, generating a tree. We define an axiom. This is our starting point for our recursion. We start with a branch. We pass down the number of maximum iterations we want. In this case, it's 7. The branch will try to do a pattern matching over the rules we have for that branch. If n, in this case, the argument is 0, then it will match this. If not, they will match this. If you have used Elixir, Prolog, Haskell, you are already familiar with this kind of thing, right? So in this case, it will match with this because n is greater than 0 because it's 7. And so the first thing it will try to do is it will output a trunk segment. So you can see here that the primitive, the symbol is a cone. It's maybe you cannot see it very well, but this is kind of a cone because it goes smaller here. And then it creates branches. And for each branch, it does some operation or transformation and then starts recursively calling branch again. And if it keeps doing this recursively over and over and over and over until our recursive iteration is 0 and we match this rule. That is commented out because this is generating the actual leaves of the tree. But I wanted to show you the tree without leaves first, so you can appreciate how it branches. If we want to see the tree with the leaves, I can just write the file. It will pick it up because I'm watching that file, and it will automatically generate the leaves. Right now, the implementation is optimized for correctness rather than performance. There are several things I can do to make the generation way faster, but since I'm touching this a lot, first I want to make sure it works properly, and then I can tweak it a little bit and make sure it's actually faster. Right? But yeah, you can see very nice tree. Some details here. So the way it works is this is a primitive, but then this is actually modifying the context we are passing down these rules. So every time one rule calls another rule, all the context from this rule will be inherited in the other rule, and this other rule can, if it wants to, it can override that context or not, right? So in this case, I'm setting the material of the leaves to be either one of these two. It will randomly pick between these two to give more variation, and so that's why you can see some leaves are a little bit more reddish, others are a little bit more yellowish, and that gives it, that just makes it nicer. It gives it more volume visually, let's say, right? The other thing I'm doing is that each primitive, in this case a sphere, can take a density argument. This is telling it to only generate this percentage of leaves on the whole volume, right? If I wanted to, I could, well, even if I don't want to, I can show you what happens if I put 1. Again, this takes a couple seconds, very quickly. Yeah, so it's not looking bad per se. It's a different style, right? But if you want something like this, sure, go ahead, be my guest, right? But I prefer the other way. Okay, so this is my L system for trees. Obviously, there are several things here that I'm doing like hard-coded in a way, because each branch branches 3 times. Now, this kind of thing can be randomized. I have primitives for randomization, for noise, from other things. I'll just show you, I'm just showing you the high-level things, or the most important things. But obviously, you can go and implement a bunch of things to make more variation and make things different. So for instance, there is a primitive for a random range, and I can say from 10 to 50 or whatever, and then pass that as one argument. All that uses always the same seed I can configure when I run the project, so it's always deterministic, which is nice. But okay, that's trees. Now, let's talk about buildings. Now that we understand how the language works, because it's very simple. Oh, one more thing. You see const and you see param. Const is just a constant. Param is an argument that I can change when I call this, when I run this grammar. So this is something to make it easier to iterate over this on the console, on the command line. So let's try with playground. Okay, so this is a building. Yay! Actually, kind of looks like the top part of those boats that go on a river. I don't know how those are called, but yeah, it could be a boat as well. Anyway, so this is a building generating procedurally using this grammar. Let me unplug this house for a moment and instead plug a simplified thing that I have. Yeah. Oh, by the way, let me so you can see the FPS is really high, but it's using all the CPU, like the processing it can. So I will cap this to 60 just because I want the recording to work properly. So I don't want the video to consume too much resources. This will cause some more noise and some details to be missed, but it's not the point right now. So I think we should be fine, and it's better this way. Let me change the sound a little bit. Yeah, that's nicer. Cool. So this could potentially be like a mega structure or something. We have an axiom. We are defining an initial size for whatever we are going to do. We are defining a default material, and then this is the first interesting thing that we have here, and we have on the tree example, which is we are splitting this bounding box. We are splitting it into 3 sections, and you can think about this kind of split, and then later on we will have a repeat. those functions act as like a flex layout, like a CSS flex layout, right? Or just a weighted layout, actually, no, not even flex. What's in here? This string defines for each of these pairs if it's going to stretch, or if it's a fixed size. In this case, this 120 is fixed. This orange part will always be 120, and then these and these will expand until they occupy all the available space. Now, these parts not only expand up and down, or in the up axis, but also scale from the center are being multiplied by 1.5. If I were to not do this, right, then the three sections will be occupying the exact same space, size on X and Z, right? And obviously I could scale this part, I could translate this by some amount, etc. Right? But the main idea I want to give you is we can split, we have a bounding box, and we can split that bounding box into parts, and how much their size is will depend on if we want to stretch them or if we want to give them some specific size. So now that you know this, let's go back to the house and let's try to understand how it works. So again, this house starts here. We are also splitting into different sections. One for the ceiling, there is this section, tiny section here. Then these stories, there are 1, 2, and 3. I put a different name for it because I wanted to do something different here, but in reality, those three are the same right now. And then a foundation, that is all those columns over there that I put them just because they look cool, and I was planning to do maybe some change in the terrain so that it will make sense, like a kind of a mountain going back down here with a slope, and then this will have these columns to make sure all the floor is leveled, right? Anyway, we have this separation. As you can see, this will stretch to whatever total size we have. So if I were to increase this, I don't know, like this. So you can see now that the space above the doors or the windows, whatever this is, these entrances, stretched up to fill in that space, and they all stretch the same distance, right? So the whole point of this is that you can change all those bounding boxes, and whatever is generated makes sense. I could make this smaller and say, well, I want it to be more like squared. Again, this will cause this part to come down, and this will be way smaller. What else do we have here? Let's look at the walls, because those are interesting. Now, when we have this story here, the story starts here. This is redundant, doesn't matter. This translate doesn't matter much. It's just so that it starts in the center. Here, there's something interesting. Each rule has some variables built in the context. In this case, each rule has the bounding box size. So this is the size in the y-axis, which is the height of that floor. I want to use this in some rules that are way down below. The easiest way is to remember this value. If you use geometry nodes in Blender, this is similar to capturing an attribute on your nodes, right? Similar idea. I capture that, and then I split the floor into, well, the actual floor space. Sorry, naming is terrible here. But the actual floor space, which is the white part, and then this divider is the brown part. For the floor part, we are doing two splits, one on X, one on Z, because we can only, as it is defined right now, we can only split one axis at a time, right? So if I were to delete this, we will see that there are two walls will disappear. Because I was basically splitting the space in this way. Fixed size, 11 voxels is this width here. Then expand all you can, and then have a fixed 11 voxels here. And that will spawn the whole bounding box for this floor. And then, what is a floor wall? Well, a floor wall is a repeated set of pieces of entrances and wall. The only thing this does is it tries to understand in which axis we are repeating things. And then what we will repeat is this wall with door. So we will have this, imagine the divisions here. We'll have something expanding here and here at each side of the door. That's why you have S and S with solid. And then here we have a wooden door. And what is a wooden door? It's also split. This time it's a vertical split, because we have the part that is above the door. This is the part that will be expanding. That it has an S, so it will be expanding. And then this 94 fixed size is actually a door that comes from a voxel model. Okay, so if I were to modify it somehow, let's say, sorry. I don't know, I'm just doing whatever. Save it. And then we reload it. Okay. And it's there. So it's very quickly to iterate and to add things to the project. And in this case, this door is our symbol, our terminal symbol, right? So we can have like programmatic procedural symbols, like spheres and cylinders and squares. We can have box files, or we can have like an actual script that does something in particular that maybe is still procedural, but if I want to optimize some part of the grammar, then instead of letting the grammar do the whole resolving the rules and all that, I may just do it manually, because I know how I want to use some things. I want to make them more performant, right? So and the last thing is, so I have obviously a repeat of cylinders for the fence of this balcony, and at the end we have this column connecting all the stories, all the floors. And this is using the variable that was set before. So this fence expands from side to side, and at the end of each side there will be a 16 voxel space where the column will go. Yeah, and that's it. Like, we can like play around with it a lot. There are lots of other functions that I've been implementing, especially for randomly distributing things on a certain surface, and other things that are really fun to do. But again, I wanted to make a quick introduction or explanation to how I do things. Hopefully it's actually helpful for someone. If you want me to go deeper into how this works, or maybe understand a little bit more about maybe my workflow, I don't have much of a workflow at the moment, but you know, I'm trying to build a workflow that makes sense. By the way, this is generated in my world, but I can output it to a box file. So if someone is interested maybe in having the box file of like this building, I can totally share it with you. Just leave me a comment or send me a message, and I can quickly generate some box file. You can even tell me like, how do you want it. I can just generate it and give it to you. That's fine. It's just an experiment. So, but if you find it useful, then be my guest. All right, that was all for today. It was probably longer than usual. I tried to speak faster as well, because otherwise I think it will be very boring. Hopefully you're still here. Well, if you're still here, you're still here. It's like survivor's bias, right? Anyway, have a good day.